Awesome. Thank you, Ben. So I'm going to talk about how to deblend the Milky Way's ISM from CGM. I personally find this topic super challenging, actually. First of all, why blending is an issue? And the answer to this question is actually very simple and straightforward. This is because we live inside the Milky Way, and it's a blessing and also it's a curse. And since this is a tutorial, I thought I'm going to cover some of the fundamental and basic terminologies for audience that are not familiar to this field. And then I will include some recent work by myself and by others for the experts in the audience as well. First of all, I want to make two analogies to illustrate why we live inside the Milky Way is a problem for us to understand the Milky Way CGM. First of all, imagine this is your house, and then your house are surrounded by a whole bunch of trees. So you live in the forest. In this case, it could be difficult for you to spot any animals like a lion, which could be dangerous because they are hidden behind trees. In this case, we say your line of sight velocity is blocked by the foreground in position space. And in this case, the foreground are the trees. On the other hand, imagine you had a really good speakers and you are playing some music. It turns out the whole universe conspired together and that your neighbors have exactly the same kind of speakers and playing music roughly at the same frequency. So you end up just not hearing a great music from yourself and you end up hearing a lot of noise. Unless somebody else starts to play piano and the piano is at a different frequency, then all of a sudden you are able to hear that piano sound. In this case, we can say the line of sight is blocked by the foreground in frequency or wavelength or velocity space. And in this case, the foreground is the sound. So for Milky Way CGM observations, we suffer both problems. Our line of sight are both blocked in position space and in velocity space because of the foreground ISM that blocks our line of sight and also blocks that moves around the same velocity. Mary has beautifully tell us about the high velocity clouds and ungaseous structures in the Milky Way. But I kind of want to show you a very simple cartoon illustration and show you why we have all these terminologies using spectrum. So imagine this is a Milky Way. We have the thin disk, thick disk, and a bulge. And then on top of it, we have the H1 disk, which has a beautiful extended arc. And then we have the intermediate velocity clouds. If you project this cloud across the sky, you see some large patches like this. There are clouds here, but this is kind of an old reference. And at that time, they don't have data in this region from that survey. So I believe this is something Filippo might mention tomorrow as well. On top of it, we might have high velocity clouds. And this is something Mary mentioned yesterday already. You also see beautiful patches and all different complexes across the sky. And if you compare these two maps together, you could see that they are not always co-spatial. And around any given lines of sight, if you take one spectrum, and this is something you might get. This is actually a spectrum I cherry-picked from the H1/4π data set and to illustrate why we have different velocity range. So you see three emission lines. At 0 kilometers per second, you see the emission line from both the ISM, the collective plane, and also the low velocity clouds. And usually we define this range using VLSR within 20 to 30 kilometers per second. And here LSR means local standard of rest, or this is the observer's reference from our vantage point at 8.5 kiloparsec from the galactic center. And going forward, we have the intermediate velocity clouds, which is traditionally defined with velocity between 30 and 90 kilometers per second in LSR. And then high velocity clouds are those with velocity higher than 90 kilometers per second, plus minus. So I said that I cherry picked this spectrum. This is because most of the time you don't really see IVC and HVC happens at the same time. For example, this is another spectrum. You see the super strong galactic emission line, but you see a teeny tiny emission line from the HVC. In a different direction towards the sky, you see IVC and the galactic emission line happening together, but you don't really see HVC. And so generally speaking, given a random line of sight, IVC and HVC H1 features do not always appear together at the same time. Why do I show you this? This is because we started to think about IVC and HVC based on H1 21 centimeter data sets. And then later on, the UV community borrowed this definition and start to look at the UV absorption lines. So here I'm showing you a halo start side line from Jess's 2019 work, where she identified this is the ISM absorption line at 0 kilometers per second, and then an IVC absorption line within 100 kilometers, minus 100 kilometers per second. In a different scenario, if you look at the quasar absorption lines, so this is silicon 2, where they identified the ionized HVCs within 100 to 200 kilometers per second in this range and in that range. And everything in this range are being very close to us from the Milky Way's ISM and this halo interface. So if I put these two figures together, there is something I have not said deliberately, but you might have figured out already, which is there seems to be a hierarchical structure where higher velocity means further distance, which is illustrated here when we think about IVCs, which is at a distance about 2.3 kiloparsec, and HVCs are typically at a distance about 10 kiloparsecs. So a few years ago, when I started working in this field, Mary, Josh, and I decided to put a question mark on this. Is it really true? And can we try to do something else to demonstrate it or to prove that it is actually wrong? So we decided to start with the UV absorption lines. And the questions I would like you to think about is, are there low velocity gas in the extended CGM in the Milky Way that is actually hidden behind a nearby ISM? In other words, are there signals in this range that is actually coming from the Milky Way CGM, but we just don't know where they are? So this is really why I am doing this tutorial today, is like, maybe there are signals blended in the low velocity regime. And in that case, how can we deblend them? For a lot of people in the audience, maybe a more genetic questions to ask is, what is the gas velocity distribution in the extended CGM if we are not thinking about all these observational constraints? So for the past few years, I have been working on this, and I have been trying to solve these problems using two different approaches. One is synthetic observations using simulated Milky Way analogs, and the other is direct and indirect observational approach. So I'm going to tell you both of them. First of all, synthetic observations. So for synthetic observations, the first thing we want to do is we want to identify a Milky Way analog. And here I'm showing you a simulation by Ryan Jones, where you are seeing the H1 projection in edge-on direction and face-on directions. What we can do is we can book a mock observer in the galaxy, but 8 kiloparsec away from the center, because this is what we are in the actual Milky Way. And then from there, we can ask, what does the off-sky projection look like from that position? And in this case, I have taken out the disk. So from the synthetic observation approach, it is really straightforward to deblend the ISM and the CGM, because you basically just take out the data from the center and then look at the rest of the simulation. And in this case, when you do off-sky projection, you can see that this is elongated structure of stretch across the sky. And this is something we have been able to see in the real data as well. You see elongated structures in large patches, even though the simulation and observation do not have one-to-one correspondence. From the simulation perspective, one question, we can ask this question directly and get the answer, like what is the gas velocity distribution? So I would like to tackle it from the phase diagram perspective. In this case, you are looking at the hydrogen density and the temperature of the CGM gas at different radii. And then this is the constant pressure line, and then this is the direction the pressure will decrease. So what I'm going to show you is the vertical blue lines are those low to intermediate velocity gas. And these are the gas that are not typically observable using real data. And the horizontal red lines are high velocity gas. And these are the gas we always talk about and we are able to observe without too much problems. So first of all, at 20 to 30 kilometers per second, you see that the low velocity gas and the high velocity gas roughly occupies the same phase diagram, except for this really hot region. And then going to a further distance at 50 kiloparsec, Now you see that the pressure decreased, and this is something Mark has talked a lot about in his model. And we see that the low and high velocity gas still occupy a similar phase diagram. And then going out to 100 and then 200 kiloparsecs. This exercise tells me that first, gas moves at a wide range of velocity in the Milky Way CGM. There are low velocity gas and there are high velocity gas. However, nearly half of the CGM gas by mass is moving at the low to intermediate velocity, and this is something we cannot observe. Therefore, this is hidden from observation. We can go one step further to ask what is the general mass flux distributions. So I worked with Forgy last year and take one of the simulations. And it is also a Milky Way analog at a relatively low mass. And then I look at the overall mass distribution as a function of gas phases. So here you see that in the gray band, these are the gas moving at low velocity with respect to the center of the galaxy. And then it actually dominates the flux compared to those high velocity gas moving at 100 kilometers per second or higher. So the takeaway point here is there's a significant amount of gas mass, regardless of gas phase, is moving at low velocity. And this is something we observers often ignore, or actually we do not have access to in general. And then now you start to see different patches, and these different patches are the velocities shifted to the observer's reference. So remember, our solar neighborhood is not in the galactic center. So we don't really get the real flux with respect to the galaxy. Everything is projected along our line of sight. So the second takeaway point here is the observed gas velocity should be corrected to the Milky Way reference. We can illustrate this problem further by counting or calculating the total inflow and outflow rate. So here I'm showing you the inflow and outflow rate as a function of phase again. And this is with respect to the galactic center. So I'm using the R to indicate the radial velocity, the radial directions. And this is a value that's not directly observable in observation. And then I'm going to shift the observer to the local standard of rest. Now you can see that the value actually changed quite a lot depending on the phase you are looking at. For the cold gas flow rate may change by a factor of 10 from that simulated galaxy that I look at, from the Milky Way's reference to the local standard of rest. And then for UV ionized gas with temperature around 10 to the 4 to 10 to the 6, in general, we see that the cold to warm gas flow rate may change by a factor of 2 from the Milky Way's reference to the LSR. So this is saying that the inflow and outflow rate estimates from the Milky Way CGM are biased due to our vantage point. And this is something Mary has mentioned yesterday, that if you think about the inflow rate and outflow rate of HVCs in the Milky Way, you really need to think about what kind of corrections in 3D models you assumed, and that might result in some difference in the numbers. So since this is syntactic observations, and I want to discuss with all of you here about like what kind of simulated Milky Way analogs we should use and what kind of parameters we should use to identify a good Milky Way analogs. We have talked a lot about mass and gas phases, so I don't want to dive into those. I'm going to focus on the morphology and the kinematics here. First of all, morphology. So this is a foggy galaxy, and I like this galaxy because it has a really beautiful warp. So this is something we have seen in the Milky Way as well. So my first go-to criterion is, if I'm going to take a Milky Way analog, I want to make sure that at least its H1 morphology is similar to what we see in the Milky Way. We can go further to analyze the radial density profile and also the density profile along the Z directions. So here in gray, I'm showing you the radial density profile from the simulations. And in red, I'm showing you what people measure from the Milky Way. So you don't see like 100% match, but overall, you see that the radial profile drops in a similar way, and the disk scale lengths are consistent between the simulation and the observations. So I think this is something that's important if you want to find a Milky Way analog, to make sure that the gas distribution are generally consistent. The other point is about kinematics. So for kinematics, I'm showing you the data here from Cabela et al. 2008. On the x-axis, you are looking at the galactic longitude, and on the y-axis, you are looking at the local standard rest velocity. And in bright pink, it means the H1 intensity is very high. You see a lot of H1 here. And then in this light green and light bluish color, you see very faint H1 or H1 that's more diffuse. So what does this figure mean? Imagine this is the Milky Way disk, and this is the center of the galaxy. And the solar system is away from the center at 8.5 kiloparsec. And it is co-rotating with the disk at a velocity about 220 kilometers per second. So in this rest frame, if we look at the galactic center, L equals to 0, there is no projected velocity from the rotation, co-rotation of the solar neighborhood. In this case, if we look at all the gas along that direction, everything will be at 0 kilometers per second because there's no projections. So this is what we see here at L equals to 0. Towards the galactic center, you see that most of the gas are centered around 0 kilometers per second because there's very few projection effects. On the other hand, if we look at something like L equals to 90, which is in a direction opposite to where our rotation is. So this is kind of like you are in a car moving on the street and you find out that you have a friend sitting in the cafe. And from your perspective, your friend is moving away and away from you, but in reality, it is your car moving away from your friend. So we see similar things in the Milky Way. At L equals to 90, we find that all the gas are moving at the negative velocity, meaning that they are moving away from us. And in this case, this is because we have the rotation velocity projected along the line of sight, and then you see everything moving away from the solar neighborhood. So from here, you can figure out that this is the positive velocity because we are rushing towards everything. And then in the anti-galactic center, we don't see anything at higher velocity because there's no projected velocity. So this is what observations of the Milky Way tells us. In a simulation, you can do something similar. So this is the simulation that Ryan worked on, and I took the simulations and built a similar galactic coordinate system and figure out that this is what the H1 looks like in that simulated galaxy. The exact values doesn't really match with the observation, but overall the rotation shape, and at L equals to 0, L equals to 90, you roughly figure out that they are the same amount of gas and the kinematics are roughly right. So this is something I want to emphasize, that if you want to use a simulated Milky Way analogs to understand the Milky Way gas distribution and kinematics, it is really important to make sure that you at least have the first order rotation right. So this is my summary one about syntactic observations, which is first, there is a non-negligible amount of mass in the Milky Way CGM, and that's about 50%. And they are moving at low velocity regime, therefore they are hidden from traditional HPC observations. And then second, synthetic observations are really useful for evaluating all these observational biases, but we have some challenges. First, how to find the most appropriate Milky Way analogs. And this is something I look forward to discussing with you all. Like, what's in your mind? That's the most important criterion you like to use to select the Milky Way analogs. And then I think different theorists might have different ideas about their own simulations, and there are systemic uncertainties in it. So from the simulation perspective, how can we trust the results of the syntactic observations, and how can we make sense of all those uncertainties? I look forward to discussing all this with you all. And now let me move on to the second approach, which is directly using observations and data. So as I show you from the UV absorption lines, I asked you the question that, are there low velocity gas in the extended CGM hidden behind the ISM? And the answer is yes, according to syntactic observations of Milky Way analogs. I want to take the question a step further to ask, how can we test this directly with the observational data? I think the most direct approach is using close pairs of quasar and stars differentiation technique. So this is a slide I stole from Hannah Bish, where you find a star and then a they are very close to each other. And then you calculate the column density difference of the two, which hopefully tell us what's the axis in the CGM. I'm not going to go into details here. Hannah has put out a really lovely video on Halo 21 new result, and it's on the YouTube, and I encourage you to go check it out. And Hannah is in the audience here as well, so you are welcome to ask her questions and have more discussions during the breakout room. I'm going to move on to some indirect approach, which is using models to understand the all-sky distributions. So I'm showing you a cartoon illustrations about what we understand the Milky Way's ISM and disk halo interface. So you have the solar system here, and it is in the ISM, and above it you have a disk halo interface that's kind of co-rotating with the ISM at a lagging velocity. So traditionally we have this flat stack approximation, which is based on hydrostatic equilibrium, where the density goes off exponentially. And this techniques and this model has been widely used in UV communities, and also Brian has used it for electron dispersion measures as well. And how does this model tell us? Imagine you have a halo star, and a halo star is at a distance about d away from us, which means it has a projected vertical height about z, which is d sine b. And then if I use the HSD telescope to measure the column density, so the y-axis here is the projected oxygen-6 column density along the vertical direction, I will get a diagram like this. The further away the star, the more material you are going to collect along the line of sight. And this solid line here is what's predicted from the flat step approximations. So basically, to the first order flat step approximation is a really, really good model to understand the gas distribution in general in the disk halo interface. And as we go to higher and higher distance, you realize that it reaches a plateau. And this is because in a flat slab approximation, the density goes off, drop off exponentially. So we don't really expect that many material at much further distance, especially for quasar measurements at z distance equals to infinity almost. We don't really expect more material to be collected. If we zoom in into this region, now here I'm showing you the galactic latitude of the quasars, because all the quasars are at distance super far away, so it doesn't make sense to show the projected distance for quasars. So in hatch region, which is blue here, the flat step model predicted a constant density distribution for all this gas because there's no variation across the sky. However, if you look at the data itself, really, the data itself gives you some weird trend, which is at higher galactic latitude, you see more projected stuff. At low galactic latitude, you don't see as much. And so this is saying the flat step geometry can't fully explain the oxygen-6 column density seen towards quasar sightline, even though this is a really good approximation from the stellar sightline data already. And I went ahead to analyze more data, and this is a different ions. Now we are looking at the silicon-4, which is on a different phase compared to oxygen-6. So here on the left, you are looking at the stellar sightline from Blair Savage and Bart Wecker, where the flat step model reproduced the data very well. And then on this regime where I'm showing the quasar data that I analyzed, you see that in general, the data doesn't really fit with the flat step really well. And so again, when we use the data, which is silicon-4 right now, we also find that the flat step geometry cannot fully explain the all-sky column density distribution seen towards quasar sightlines. And so this is, I believe, the indirect evidence for an extended CGM beyond the flat slab. So I decided to went ahead to build a really simple model for the Milky Way CGM, which is an extended CGM, and it is only accessible to the quasar sightlines. And my model is built upon the flat step geometry, and I decided to just adding a super simple constant density profile in a CGM and to see whether it works. And around the same time, Zhijie decided to build upon this model and have a more sophisticated density distribution where it is depend on the radial and also the z directions. At the same time, it has a kinematic component in it. So I'm going to show you how this different model differs and what consensus we have been able to reach. So this is the silicon-4 column density distribution as a function of galactic latitude, as I showed you earlier. The flat set geometry predicted a plateau for everything, which you can clearly see does not match with the data very well. And then my model, which is a really simple constant density model that has an extended CGM, that is able to largely recover the column density as a function of galactic latitude. And on top of this, Zhijie's model, which has longitude dependence in it because of the radial dependence, now you can see that along different directions, you expect to see different column density as a function of galactic latitudes. So the takeaway point from this comparison is an extended CGM component is necessary to explain the UV data, either it's oxygen 6 or silicon-4. However, model details might differ depending on what you put into the model. So this is my summary point 2. First of all, we have the Quasar data, and I did not go into details about it later, but I look forward to Hannah telling us more during the breakout room sessions if people are interested. And my work shows that an extended CGM component is necessary to explain the UV data. However, we need to talk more about what kind of details have been put into the model. Zhijie is in the audience, I believe, so I look forward to hearing more from his perspective. We have a lot of challenges in this region as well. For example, the Milky Way CGM at low galactic latitude is largely inaccessible. So we have to figure out a way to understand that part of the CGM. And on the other hand, even though we find that the extended CGM is necessary, however, from our Quasar data, we don't actually see that much CGM access if you compare nearby Quasar pair sidelines. So perhaps we need more sophisticated model with non-spherical gas distribution in the CGM. So this is something that haunts me all the time, and I love to hear your thoughts, like what kind of models you have in mind and what we need to do to figure out the general Milky Way CGM gas density distribution. With that, I'm going to end here and take questions, or we can all go to breakout rooms and have a discussion. Thank you.
Okay. Thank you, Jan. That was great. What we'll do now is, take a couple more minute question, 2 or 3 more minutes, maybe one question here, and Jess has her hand raised, and then migrate over to the breakout room.
That was beautiful, Yong. I really, I love the way that you explain our perspective. And so I always get turned around when I think about local standard of rest versus galactic standard of rest. And I think, you've explained this to me before, but I just want to ask a very straightforward, I feel like I know how to pose the question now. So if you look at the Calberla, is that how he said it? Is it Calberla? 2008.
I guess so.
H1 velocity distribution, where like you're looking toward galactic center, and the line of sight velocity is 0, but you're always up at some galactic latitude or whatever, so it's a projected velocity. When you put into the galactic standard of rest frame, are you basically subtracting out that kind of velocity shape, or does rotation have nothing to do with galactic standard of rest?
Yes, this is a good question. So my understanding is galactic standard of rest corrects that rotation, projected rotation, whichever direction you are looking at. However, there is a difference between you correct the value or you correct the velocity vector, because the galactic standard of rest still, the velocity vector still points at the local LSR. Even though you have corrected the velocity, you're not able to point the velocity vector to the Milky Way center. So I think the galactic standard of rest does not really reflect what's going on if you're able to migrate to the Milky Way center and see it there, because it only corrects the projected rotation. Does that make sense?
Yeah. Okay. So if I'm trying to understand, for example, like velocities that I have, line of sight velocities that I have toward, halo stars or quasars or whatever, in the context of the Milky Way, and I want to know, like, kinematically what's happening, is it easier, in your opinion, to just look at the local standard of rest and then just kind of have that rotation in mind and do that more visually in terms of that comparison?
This is a great question. I think different people might have different opinions on this. To me, I think local standard of rest is easier because I know this is with respect to LSR and my observing rest range. And the galactic standard of rest, the name itself is a little misleading. Therefore, it's not straightforward because it corrects the projected rotation, but it does not correct the velocity vector. So sometimes I often got confused because I thought it's galactic standard of rest, so it must point towards the Milky Way center, but it's not that case. So I think Josh has a really good model in his review paper with Mary, like Mary Prockman in 2012, where they did build a 3D model to correct for that. Mary, correct me if I'm wrong. My impression is they did a 3D model to try to account for that effect. Yeah.
You mean for the inflow rate?
Yes. Yeah.
Yeah, Josh set that up in terms of it having different motion components and then what you would actually get for the inflow rate. There's also the deviation velocity can always be used if people want, where you basically deviation velocity is how much the velocity deviates from a simple model of galactic rotation. So that kind of gives you have a simple model of galactic rotation in mind, and then you immediately see where all the gas is relative to that. So that can be a more intuitive type of velocity to use, and that's why I think Bart Walker set that up at some stage originally in his oldest review, and it's been useful. You do have to be careful in terms of what you use for that model of rotation for a galaxy, but it can be a useful reference point.
Oh, great. Yeah, I like that idea. Thank you.
Okay.